Here, in the lowlands of Lancashire, in an area called the Find, a few miles from Blackpool, lies the Preston New Road drilling site where shale gas was to be exploited. Back in 2011, there was a great deal of optimism following the success of shale fracking in the USA, and it was believed that hundreds of trillions of cubic feet of gas in this area could restore energy independence, provide cheaper gas, and create thousands of jobs. 14 years on, the only thing evident is the drilling rig platform. And not a single kettle has been bored with English fracked gas. So what went wrong? Protests, minor earthquakes, and public concern all certainly played a part in halting the shale gas revolution in Britain, but the main problem was geology. Quadrilla drilled down 2 kilometres into a thick layer of shale. It's a rather boring rock, grey, and composed of cooked-up mud and silt. This rock formation is found at the surface at the base of the nearby hills further east, named the Forest of Bowland. While the area is now largely devoid of woodland, its name comes from the medieval term for a royal hunting preserve. The hills themselves are younger, it's millstone grit rocks, but at their base there's a shale layer which is visible. Now, the shale stretches east and south into Yorkshire and the Midlands, and to the west of me the same strata extends beneath the Irish Sea and beyond the Isle of Man. And there it reaches a depth of up to 7 kilometres below the surface. What made Bowland Shale so attractive to frackers was its remarkable thickness, ranging from over 100 metres to 600 metres. Now, in contrast, the US shale plays, the US shale gas fields, range only from 30 to 100 metres thick. So despite Bowland's much smaller geographical area compared to the vast shale plays of Texas, it contains a large amount of gas in a compact space. Bowland Shale at the surface isn't very exciting. It's been exposed to the elements for millions of years, and any traces of hydrocarbons or gas are long gone. But I can bring you here to a place where we can truly explore the depths of Earth's past. This is Kimmeridge Bay in Dorset, and these cliffs are made of Kimmeridge clay. It's a rock, so don't let the name fool you. I'm going to use it as an example. It's much younger than Bowland Shale and has a flaky texture that's quite distinct. What's special about these cliffs is you can actually smell the fossil fuels trapped within this rock. There's so much organic matter that you can literally set it on fire. Hundreds of years ago, local monks even burned this rock as a low-grade fuel, a sort of primitive coal.
Shale.
Where I'm standing now, during the Jurassic period, about 150 million years ago, was once the floor of a deep tropical sea. Mud was washed into the basin, and countless sea creatures lived their lives here. Now, for the lay geology enthusiast, the mind-bending timescales can be hard to grasp. Not just millions of years, but hundreds of millions, even billions. But here is a moment frozen in time. Right here in the rock are animates that died and sank to the sea floor, where they were fossilized. So, sorry to the fans of alternative ideas like a biogenic oil, these cliffs are proof of fossil fuels formed from organic matter. Now, not from dinosaur bones, or indeed the animates themselves, but the vast amounts of plankton, algae, and organic debris mixed in with the mud. Think of it as the black slime you find at the bottom of a garden pond or a quiet stream, an organic rich black soup. Now, over millions of years, vast amounts of this sediment get compressed under the weight of the sediment above, squeezing out the water. The slow process of turning slime to rock begins. How slow? Well, London clay beds, used for brick making, are over 40 million years old, and they've never turned to rock.
quite waxy. But yeah, you can see it's got a slight shine to it.
Now, with more time and more pressure and some heat, the organic matter transforms into kerogen. It has a waxy look and feel, but this rock is not pure kerogen, it's mixed with fine salts and clay. Kerogen is the first step to oil and gas. It's a complex hydrocarbon, much like the complex carbohydrates in our food, which we break down into simple sugars and proteins. Given the right combination of heat and pressure, kerogen breaks down into oil and gas. Bowland Shale, buried deep underground, went through this oil window of cooking. But it didn't stop there, and the process continued to generate mostly methane gas. Now, these gas molecules are trapped, and they're tiny, and they're locked in the actual rock structure. So this kerogen rock is really quite waxy to feel, and behind me is the remnants of the Scottish shale industry. The great slag heaps left over after they cooked up shale. Man-made hills in Scotland that tell a remarkable story. Not only do they mark mankind's early exploitation of fossil fuels, but they also reveal the energy potential hidden in shale. Back in the middle of the 19th century, a Scottish chemist named James Young, born in 1811, developed a groundbreaking process around 1850, and he discovered how to turn naturally occurring coal tar into useful oils, the most important being candle wax. When he returned to Scotland and patented his ideas, he built an industry to exploit the fossil fuels locked in shale found around here, and they're often associated with coal deposits. Young devised a simple but very energy-intensive method to reproduce in a fraction of the geological time the natural process that turns shale into oil. By heating the shale, he could extract oils, and mainly paraffin for lighting. But placed, say, in a vessel and heat up, it will drive off the oil, and this can be condensed. A problem with the method is that it used far more energy than the oil it produces. But in Young's time, coal was abundant and cheap for cooking up the shale, and oil for paraffin and lubricants was far more valuable. Young's industry continued into the 20th century, lasting right up to 1964. Over time, the process became more efficient, even powered by burning the oil shale itself. The waste product left behind was this pinkish shale, the kerogen extracted, and it leaves a soft, crumbly, biscuit-like rock. From a ton of shale, about 80 kilograms of oil could be harvested, heating the rock to 500 degrees C. Today, these shale wastes have been piled high into these distinctive Five Sisters bings, as they're called, that dominate the local landscape. And they're a bit of a monument to human ingenuity and industry, a landmark of a past when shale oil was king. It may be obvious that I love travelling and exploring geological sites, but my journey from the south coast of England to the central belt of Scotland actually spans 150 million years. The shale associated with the coalfields of Scotland is quite different from the Kimmeridge clay in Dorset. Now, without wanting to confuse you further, it's interesting to know that Kimmeridge clay here once stretched as a Jurassic shallow sea all the way up to the North Sea and beyond, and into the Norwegian Sea. And this Kimmeridge clay formation is the primary source of rock for much of North Sea oil. As I mentioned before, geology is Earth's autobiography, a rich and fabulous story, and Britain is blessed with some of the most amazing chapters. The best part, anyone can explore these pages of this epic tale simply by taking a nice healthy walk in the countryside. Britain is rich in geology, but it's often very complex and sometimes very confusing. To explain it simply, imagine hundreds of jigsaw puzzles from charity shops, all with missing pieces, some mixed together, none with a picture on the box, and over the years, geologists have painstakingly separated these pieces, fitting them into the right puzzle, and filling in many of the missing parts. Not bad for monkey people over the last couple of 100 years. As a filmmaker and geology enthusiast, I want to do more than just explain why the UK shale gas revelation never took off. I want to climb into that time machine and transport you back to a very alien world, some 325 million years ago, when Britain lay on the equator and Earth was a very different planet. And this is when Bowland Shale was first laid down. So let's go back in time. If you imagine where I'm standing on this beach is the present, and the far end is the beginning of the creation of Earth, we can make our way to the Carboniferous. I stop here because that very short distance is the entirety of our oldest human ancestor. I'm going to stop 60 million years ago. The Victorians named the Carboniferous as the coal-bearing period, but it lasted 60 million years. To put that into perspective, 60 million years ago was the end of the Cretaceous. The Atlantic was only a few hundred miles wide. America and Greenland were a lot closer together. The northwest of Britain was a volcanic zone. Dinosaurs roamed the Earth, and soon they would be wiped out by an asteroid. Mammals were just starting to get their lucky break. The Himalayas didn't exist. And in that short 60 million years, we're now. The Coal Age was just the last 20 million years of the Carboniferous period. And shale gas slightly predates it. Now, as you notice, we've passed the Carboniferous age into the Devonian, but there's a reason, and it gives an answer to why a narrow, deep sea formed in the north of England. Right now, we are well south of the equator, between 490 and 390 million years ago. The little microcontinent Avalonia that carried England and Wales was slowly catching up with Laurentia, and the Iapetus Ocean was being consumed and subducted beneath these land masses. So all of this was happening in the southern hemisphere. The equator to the north was here, and the great big Gondwana continent was to the far south on the South Pole. Laurentia had broken away, and Avalonia, the microcontinent, was chasing, and the ocean was being subducted below these two continents. As it did so, volcanic activity, which is the Lake District and Snowdonia, were bubbling up. Eventually the two collided to form this soft suture. Remove these volcanoes for the time being. And this was an inherent weakness. This soft collision, about 420 million years ago, swallowed up the ocean, and a great mountain range rose up in Scotland, Greenland, and Nova Scotia in Canada. The remnants of that lost ocean can be found along this short stretch of the eastern Irish coast. Geological scar, and it's known as a suture. It's a scar. It's a place of weakness in the Earth's crust. The Great Caledonia mountain range quickly eroded back down, thanks in part to the tropical climate. As the rocks were crushed and compressed, building up into a mountain, quartz-rich rocks in the continent were pushed up, eroded, and then transported by rivers to create vast sandy plains, now preserved as old red sandstone, and we can find it in places like the Brecon Beacons and Exmoor. By the time the Caledonian Mountains had worn down 400 million years ago, the great supercontinent of Gondwana was approaching. Colliding with Avalonia and Laurentia, it formed a new mountain range called the Vascaran. Traces of this mountain building event can be seen today in the far southwest of England, on the Lizard Peninsula, and in the Ardennes of Europe. The impact was felt along the Devon coast, Pembrokeshire and southwest Ireland. It's a geological crumple zone where rock layers were folded and buckled. The Vescaran mountain building event was a long and slow process over about 100 million years, and it had a massive influence on today's landscape. The Devonian, the time of fish, and the planet and Britain passed through dramatic climatic shifts, cycling from desert conditions to ice ages and then back to tropical environments. To the north in Scotland are the Caledonian Mountains, and to the south the Vescaran. And in between, this mountain building set up a kind of geological Mexican wave as the Earth's crust warped and flexed. Horst and Graben is simply German for ditch and heap, and it's ridges and valleys, basins. So this happens on this occasion because we've got you have to imagine these are the Caledonian Mountains, which were pushed up 400 million years ago, and then the younger 300 million year old Variscan Mountains, which have again disappeared. Their weight is pushing down into the Earth's crust, like two fat asses on the sofa. In between, the crust is being stretched, and if it gets stretched, well, some get pushed up and some go down. In Devon, the land was pushed up. To its north in South Wales, the land sank. To the north of that, the Brecon Beacons and Wales were pushed up. And then in northern England, a series of blocks dropped down, creating an enormous Pennine Basin and the sub-basins of Bowland and Craven. And then even further north, the ancient Silurian rocks of Scotland's southern highlands were uplifted, and to their north, the central belt of Scotland, from Glasgow to Edinburgh, experienced subsidence along existing faults, and the land sagged. This can be currently seen in the US, where a weakening of the crust in the southwest of the continent displays a series of valleys and peaks, clearly visible and occurring over the last 17 million years. The Pennine Basin, with the Bowland and Craven sub-basins, follows the ancient scar in the Earth's crust, the suture zone of the collision between Avalonia and Laurentia. As Avalonia impacted Laurentia, the microcontinent lost all its energy, and a weld was made, but early on it was a weakness, a crack that descended to the mantle 30 to 100 kilometers deep. Now that's stabilized over time, and this soft docking is a head-on collision, technically known as orthogonal, which is quite different to the oblique angle collision of continents seen in the Great Glen Fault, which is still slowly moving past each other. And that's equally deep, and that scar has not fully healed, meaning there's the occasional minor earthquake. The geology beneath the Pennines is not random, but an outcome of ancient continental collisions inscribed in the rock. And these early tectonics set the stage for our much later landscapes. Look out from North Wales into Lancashire and Yorkshire, and you would have been looking out over a narrow but extremely deep sea that connected to the Greater Ocean to the west. At its southern edge here, shallow tropical tributaries fed into the sea and corals flourished, building these thick limestones of the Great Orme. Now, the uplands of central Wales were lush tropical forests blooming with ferns, mosses and horsetails. Although we've entered the Carboniferous period, it will be millions of years before the great coal swamps begin to form in South Wales, elsewhere in Yorkshire and the north of England. Here on the island of Arran in Scotland, these limestone rocks have been buckled 45 degrees and shaped by tectonic forces. But once they were the muddy floor of a tropical forest near the equator, and the mud here rich in calcium carbonate, making it the edge of a lagoon teeming with corals tens of thousands of years as sea levels ebbed and flowed. A giant centipede, an Arthropleura, 2 meters long, left little footprints here 326 million years ago. Dragonflies, the size of pigeons, filled the air. Oxygen levels were high, so at least you could run fast to escape these monsters. The atmosphere was humid and hot, filled with CO2, nourishing abundant plants and animal life. And crucially, soil became a thing. Now, in the dry Devonian desert-like landscape of Britain, soil was sandy, perhaps silty, but generally poor. There was very little in the way of land life. Now, good soil contains clay. And clay is not just fine sand, it's chemically altered, superfine material that forms flat, sticky plates. These plates slide and stick to each other because they carry an electrical charge. And I'll probably do a full episode on how amazing clay is one day. Suffice to say, the warm, humid conditions of the early Carboniferous, with plant roots growing through sands and silts, created a lot of clay. Mixed with the remnants of plants and animals, washed into streams and rivers, this clay poured into the Great Pennine Basin. Now, in shallow seas, nutrients from dead organic matter would recycle into new plants and animals, but this deep sea was still, with few currents and very little oxygen, and a perfect place for organic matter to transform slowly into hydrocarbons, with the first step being kerogen. Towards the later part of the Carboniferous period, around 320 million years ago, the Pennine Basin began to close, and this was not just a sudden tectonic squeeze, but a very gradual process involving both the mountain building activity and sediments filling up this sea. Activities during the Vaskaran, orogeny, caused some uplift and deformation around the basin, gently squeezing it and reshaping the land. At the same time, vast amounts of sediment were washing down from the newly uplifted highlands to the north, probably areas corresponding to Scotland and the Lake District. These sediments are known as millstone grit. It's a coarse sandstone deposited by powerful ancient rivers and deltas. Millstone grit sediments filled the basin over time, forming extensive deltic deposits and progressively shallowing the deep marine environment. This process contributed to the basin's gradual closure, transforming it from a deep sea into a more terrestrial and deltic environment. And we can see traces of that landscape today. Now, the marine sediment, laid over tens of millions of years, was anywhere from 1.2 to 1.8 kilometers thick. That's a mile of mud. But as it was compressed and covered, it reduced down to 600 meters, thickest part of the Boland Shale. The pressure and heat cooking up the kerogen into gas and the soft sediment into shale. So the frackers found a challenging clay, and it's called smectite. It's a clay that has a tendency to swell when it gets wet. This smectite didn't just appear out of nowhere. It formed under very specific conditions in this sea. And smectite is often formed from volcanic ash. The marine basin allowed for volcanic ash from atmospheric fallout to settle. Some of this ash may have come from distant volcanic sources, but there was also more local contributors. There is evidence of small-scale volcanic activity and traces found in Derbyshire, the East Midlands and South Wales. And then there was also sediments washing in from nearby uplands, like Snowdonia and the Lake District, where older volcanic ash had weathered and transformed into clays like smectite. And smectite clay is self-healing. When it gets wet, so the very act of fracking caused the cracks to self-heal, and hence the flow rate of gas, and impacting the operation's profitability. The shale resources in Scotland's Central Belt, which have been under review, are likely to have even more ash-derived smectite given that Arthur's Seat in Edinburgh is associated with a volcano that erupted during the laying down of these shale sediments. So why is British shale different to the US shale plays? Well, the Midwest flyover states of the US are geologically boring. Unlike Britain, which has a thick lasagna of strata, but one that has been squished about with, reheated, added to, and messed around, the geology of the US and its shale is more like a pizza, neat and thin and vast. Like Bowland Shale, it formed as organic-rich sediment, but unlike Britain, the sea was wide and vast, with most of the marine matter deriving from marine life. So there's less clay, and there's more brittle silicates and calcium carbonate came from marine creatures and plants, the difference between a biscuit and a thick, soft cake. And indeed, Bowland Shale is quite different to Kimmeridge clays that have delivered an abundance of oil and gas. While both Kimmeridge clay and Bowland Shale are rich in organic material, they have different clay mineralogies and the environment. You can see here at Kimmeridge there are carbonate-rich strata of limestones, and it's moderately clay, very brittle, and it becomes an excellent source and sometimes reservoir oil and gas. Recently, other basins, such as the Gainsborough field in Lancashire, keep the fracking dream alive. Whilst it remains a target of interest and excitement, the Gainsborough Trough is generally understood as a component of the larger Pennine Basin, and it's likely to suffer from many of the same production challenges. I set out to explore UK shale gas, better understand why it failed, but also to address a peculiar form of energy populism. That despite the UK peaking in gas and oil and coal, there is this persistent belief that there is still untapped fossil fuel resources. Robert Jenrick, who seems to be campaigning to be the next Conservative leader, made this promo. It's a flag-waving, patriotic call concerning British oil that powered the RAF in the Battle of Britain. No, after a rather long-winded history lesson. The point was to protest about the imminent requirement of Credrilla to make good on their planning application, to fill the wellhead with concrete to avoid pollution of leaking methane. But it was all under the guise that it was some kind of madness to terminate the option for future gas. The company had successfully delayed the expense of making good under Boris Johnson. Robert Jenrick did tap into the notion that the UK still has unlimited fossil fuel resources. Scientific fact, however, paints a far less optimistic picture. Geological surveys and exploration wells show that Bowland Shale and other UK formations are thick but complex and rich in clay, and far more challenging economically and technically than the easy shale plays of the US. The North Sea, once a bonanza of conventional oil and gas, is now in decline, with remaining fields tiny compared to our consumption. Some estimates suggest that even the entirety of the undiscovered and undeveloped conventional fields may add an extra week of UK gas demand. And all the while the UK relies on imported gas. Economics tell a similar story. Developing the shale resource in the UK would be expensive, technically risky, and at best only partly offset import. The UK cannot rely on fossil fuel renaissance to solve its energy needs or climate commitments. So, why the persistent cheerleading? It seems to be a mix of energy nationalism, political populism, and vested interests, shaping a narrative that paints fossil fuels as the key to independence and prosperity. It's a comforting story for some politicians and companies that profit from that hope, even when the science says otherwise. An aspect of populism is that somehow there's a bad guy who is stopping us reaching our full destiny. On this occasion, it's environmentalists and scientists, but they're not stopping progress. They're simply warning us about energy realities and climate limits based on robust evidence. So, I really hope you enjoyed this video. Do like, comment, and subscribe.